Hi everyone, welcome to lecture 22. So last time we saw how to construct one of the two ingredients for proof composition, specifically robust PCPs. We essentially did it generically through two operations. First, you bundle queries using essentially logic extensions and manifolds. And in the second step, you use a good code to kind of take a large alphabet and go over a small alphabet, while gaining at the same time robustness. Okay, but this was only one of the two components. For proof composition, we also need PCPs of proximity, and that is exactly what we're going to look at today. We're going to construct PCPs of proximity. So just to remind you, a PCP of proximity is to prove for a given instance X and a candidate witness W that W is close to a valid witness for X, if one exists. Of course, if none exists, then everything is sort of by definition far. But syntactically different from a PCP, the PCP verifier, a PCPP verifier has oracle access to both. I still have the same typo here. Oracle access to not just the proof, but also the given witness whose proximity is being tested. Okay? Now, some notation, because we're going to be using it today. Remember that PCPs of proximity, they are for relations, not languages. A relation is just a set of instances of witnesses that come together in pairs. So you can think about it as, for example, circuits and satisfying assignments. You can project on the first coordinate, you're going to get the corresponding relation. So in the case of circuits and satisfying assignments, you project onto circuits that have a satisfying assignment. And then for a particular instance, you can look at a set of witnesses. Those are all the valid witnesses. And of course, if the instance is not in the language of the relation, then the set of valid witnesses is empty. The definition of a PCP of proximity, we saw it carefully sort of 2 lectures ago when we talked about proof composition. Sort of the strength of the PCP of proximity is given by the proximity parameter. In the good case, you say that because the instance and witness are part of the relation, in particular the witness is valid, is of distance 0 from a valid witness, then the probability the verifier accepts, given oracle access to the witness and the PCP of proximity, the one constructed by the honest prover, is say 1. Okay? Whereas proximity soundness dictates or requires that for any instance of witness, if the witness is delta far from any valid witness for that instance, then regardless of the proximity proof, the verifier is not going to accept with high probability. Okay? So that was the requirement. Now notice that unlike for robustness, where you want the robustness parameter to be as large as possible, for proximity, for the same soundness error, you would rather have a proximity parameter being as small as possible, right? Because this is kind of the condition under which something kicks in, right? So robustness is you want it to be large, proximity parameters you want it to be small. This is of course for a given soundness error. Then of course there are trade-offs that if you can make this for any particular construction, you can try potentially to make the robustness parameter smaller. That might reduce your soundness error, and you can, for a given construction, you may increase the proximity parameter, and that might reduce your soundness error. Okay, but for the same target soundness error, you want large robustness and small proximity. Okay. This is the picture. Wind yourself the 2 oracles. And today we're going to show to construct 2 types of PCPs. We're actually going to be using them both in proof of composition. One is we're going to construct a exponential size constant query PCPs of proximity for quadratic equations. For simplicity, we're going to be looking at over the Boolean field rather than just arbitrary fields. So this is saying that you can choose any, let's say, constant proximity parameter. So here it is, and you're going to pay for it somewhere. So for example, here in the number of queries. But again, for any constant here, this is going to be a constant. Okay. And we're also going to show something incomparable. And again, we're going to be using both of these in proof composition. Polynomial size PCPs of proximity with polylogarithmic query complexity. These essentially are the proximity variants of the two types of PCPs we've seen, okay? Exponential size constant query or polynomial size polylogarithmic query, okay? And we want to understand how do we make, both of those proximity variants, okay? Questions so far? Okay, that's kind of the goal for today, and then towards the end of the class we'll actually go through the motions of proof composition to derive the PCP theorem, because we'll have all the necessary pieces. We good? All right. So just to be precise, I have written the strings Q, E, S, A, T, F before as a language, but today I specifically mean the relation. Okay, so the instance of equations together with the assignment that satisfies it. Okay, so I'm not gonna make up some different notation just for the relation. Today we're specifically talking about the relation. All right. So first, before we get to construct these objects, because they're syntactically different from a PCP, we need to understand how they compare, okay? Because it could be that, who knows, maybe proximity soundness is not a strengthening of normal soundness, is like different. And so if it's different, then, we should go in that direction, okay? But even though PCPs are syntactically different, PCPs of proximity are syntactically different than PCPs, I want to convince you that there is a very clear sense in which there's stronger notions. And so we will have to work at least as hard as constructing a PCP, okay? So that means that, if anything, we have to start from where we left off and continue from there, okay? So one particular way to kind of encapsulate this sort of they're at least as strong is to say, okay, well, give me any PCPP for some relation for whatever parameters. And right now, it could be any proximity parameter. I'm going to show you how to construct a PCP with basically the same parameters for the corresponding language. So this is saying that, look, to the extent that I work hard to go here, I worked at least as hard to go here. Okay? And usually the length of a PCP is at least the length of the witness anyhow. And so this is saying that, yeah, PCPs of proximity, while syntactically different, they are stronger, okay? So this is also an exercise in terms of definitions, just to kind of become familiar with them. So let's show this, it's a simple proof. So give me the PCP of proximity. So here it is, it's the one I start from for the relation. We want to construct the PCP, not of proximity, just normal PCP for the language, right? So how is it going to go down? Well, you have the prover and the verifier for the PCP you want to construct. And what are you going to do, right? So you can find the witness for X. Remember that, we're considering a language derived from a relation. So just find the witness for X, or you can always receive it as an auxiliary input. That's always possible for a PCP, right? So, just for a zero knowledge proof or whatever, you may have even though you're talking about language, the honest prover may receive an auxiliary input, the witness, okay? So just find a witness for the instance. And compute the corresponding proximity proof, okay? Even though today you're not about proving proximity, just pick any witness that is valid and construct a proximity proof for it. So now your PCP is the witness and the proximity proof. That's your PCP. That's where this kind of extra length comes from. So that's your PCP, looks like that. And what are you going to do? You're just going to run the PCP proximity, okay? Notice that, syntactically is a little bit different because the PCP proximity kind of wants to think of this oracle and this other oracle as different oracles. You're given one oracle, but that's okay. You can, think about it as two oracles, right? So there's nothing sort of stopping you from doing that. Completeness, well, if X is in the language and there is a witness, you will find the proximity proof will make the proximity verifier accept with that probability. Now, if X is not in the language, then crucially, all candidate witnesses are far from Rx because it's empty, okay? So it means that whatever candidate witness a malicious verifier writes down, guess what? It's going to be delta far from a valid witness because there are no valid witnesses. And 1 is greater or equal than delta for any delta, okay? Even if you have a really crappy PCP of proximity with a really large delta that is not even bounded away from 1, that's okay, that's good enough, okay? And so the condition kicks in, and you're gonna kind of reject with high probability. Okay, so this is telling you that, yeah, PCPs of proximity are at least as strong as PCPs, so we're gonna have to work just basically harder, not in a different direction. Okay, this is important to understand, right? So it kind of calibrates your expectations. Any questions about this proof and kind of why we went through this simple exercise? Notice that for robust PCPs, it was easier to spot that they were stronger because we didn't really change the object we were talking about. Here, for PCP proximity, we changed the syntax, so it wasn't like say completely obvious they were stronger, right? Okay. Okay, that's what we said. It's also what we said. So we're going to have to work at least as hard to construct PCP proximity as we did for PCPs. All right, well, if this is the easy direction, then it doesn't mean that we don't have to work at all in the other direction. If we want to go from a PCP to PCP proximity, we're going to have to do something more, okay? Now, we're not going to see a generic way to do it. In fact, in general, I'm not aware of any sort of generic way of going there. But we're going to see some basically paradigms. We're going to see how certain types of PCPs, specifically all the ones we have seen in this class, can be modified suitably to kind of lift them to be PCPs of proximity. Okay, like all the PCPs we constructed were for some underlying relation anyhow. Okay, and if you remember, there was basically a witness that was participating in some encoded form as part of the PCP, right? We had a recipe, we constructed a PCP in two parts. There was usually kind of the encoding and then some satisfiability proof, right? The encoding was allegedly encoding of some candidate assignment or some candidate witness, right? That belongs to some set of well-formatted things. And then, if, through a proximity test, we established that this part was close to some valid encoding, then this other proof was helping us check that the witness was valid. Right? This was our format. Okay, this was the template, for every single PCP we constructed in this course. Not just PCPs, also IOPs, by the way. Now, if you go back to the soundness analyses, how did we prove soundness? The reasoning that we used actually showed more than soundness. What it showed was a property that goes something like this: that if the PCP's verifier accepts with high enough probability, above the threshold that, the soundness error that we proved, then what we actually learned from those soundness analyses was that not only X is in the language, therefore we cannot be in the soundness case, but also specifically we learned that this first piece of the PCP was close to some valid encoding, was close to an encoding of a valid witness, okay? That was actually what we showed in all of those soundness analyses. Okay, so you can actually encapsulate this in a property. We're going to say that a PCP verifier is epsilon delta enc sound if for any kind of written down PCP of this format, if your verifier accepts above a threshold, then there is a valid witness that is close to the thing that was supposed to contain the witness. Okay. And basically, all of our soundness analyses that we've had in this class, show you this. That was true for everything we've done. Okay? Okay, so that gives us a handle, right? It means that, all right, so we have a PCP that talks a little bit about valid witnesses. Because remember, in a PCP proximity, we're going to be interested in measuring the distance from some candidate witness to a valid witness. Now we know that if we start from a PCP of this sort, at least we have a valid witness somewhere, and maybe all we're left to do is to measure the distance between them. Okay? And that's indeed what we're going to do. So for PCPs of this sort, there is basically a template construction of a PCP proximity from a PCP that has this property. Intuitively goes something like this. Again, this is at least still at high level. You're going to compute this kind of two-part PCP using this PCP that has two parts, using the witness W, the one that is given to you here. And then we're going to somehow come up with proofs that are going to be a consistency test. Okay, consistency test for what? Well, okay, I have it in a few clicks. The consistency test is going to be to convince the verifier that the witness that is given to the verifier is consistent with the witness that is encoded in this first part of the PCP. And maybe to convince the verifier, we're going to need some proof to do that. So put it there as well. So now the verifier is going to get a proximity proof that is made up of 3 parts. 2 parts coming from the 2-part PCP, and a 3rd part to help the verifier establish that the witness that it actually has is consistent with the one that is inside here. Okay? So what it's going to do? It's going to run the 2-part PCP, and it's going to run the consistency test. Now, what property intuitively do we want of the consistency test? It's this property. We want that if W, the one that I have, is delta far from W tilde. Who is W tilde? W tilde is the thing that is inside pi A up to noise. Okay? If both of these conditions hold, then I want my second test to pass with probability that is small, right? Because what's the plan, right? So if this is my verifier, 2 things can happen. Either the PCP verifier accepts with small probability. That means we are in the case where X is not in L, right? Because regardless of proximity, if X is not in L, we can rely on the PCP verifier to help us. So the only problem is that when the PCP verifier accepts with high enough probability. But when it does, it means that we are in L and that pi A contains a valid witness. So now I am only left to kind of reject with a probability that goes up as the distance from W increases from any valid witness, in particular this one. Okay? So if I know that W is delta far from all valid witnesses, it certainly will be delta far from this valid witness. So I am left to basically kind of compare these guys. Okay? Now, this is just a high-level intuition, and we're going to turn this, to something concrete in the next slide. But is it clear what the plan is? Basically, we're going to exploit the structure of PCPs we've built, and then we're going to augment those PCPs with a test that is going to compare the valid encoded witness against the witness that we do have that in the soundness case is guaranteed to be delta far from all valid witnesses. Okay? Questions? Okay. All right, so let's turn this template into a concrete construction. So we're going to be using, local decoders. We've seen them twice before. Once in class for exponentially large PCPs. Okay, that was locally decoding or self-correcting linear functions. And the second time you've seen it in homework. Okay. So I'm going to give a generic definition of a local decoder, and I'm going to show you how, given a local decoder, we can construct a PCP of proximity for such PCPs. And then we're going to just come back and say, okay, well, we have local decoders for this and that types of encodings, and so that is going to give us PCPs of proximity of the 2 types that we've seen, that I've stated at the beginning of the lecture. So in general, we say that D is a local decoder for an encoding enc, or in general a code, it's the same thing, with decoding radius delta LD and error probability epsilon LD, if 2 things hold. Well, first, if you give me a valid encoding of the message and I give you any index, I'm able to reconstruct it from the valid encoding. Okay? And you should think of this local decoder as being local. It makes a small number of queries. The other direction says, if you give me some noisy code word that is not too noisy, well, how not too noisy? Well, delta LD close. Then I'm still going to be able to recover it, but I may have some error and it's bounded. But this is true for every single index, okay? For every single location of the message, okay? So, and this should kind of sound familiar. This is basically what we did with kind of linear functions and low-degree functions. In fact, actually, we've shown something stronger. Not only can you recover the message, you can also recover any position of the code word itself. So that's something known as local correction, not local decoding. But whatever, you're going to need just local decoders. And if you do have a local decoder, actually we'll even be able to do a PCP proximity without even using an auxiliary proof pi-e. We're just going to be able to do an extra test and that's it. Okay, we'll use pi-e later on after that for other reasons. So here's what I'm going to show. If you give me some PCP that is epsilon delta enc sound according to the definition earlier, and whatever parameters, and also the enc under which the witness is encoded has a local decoder with the coding radius that is above this distance here, and some error probability, then we have this kind of smooth construction that for any proximity parameter you want and any epsilon soundness error, I can construct a PCP proximity for the relation underlying the language. With some error, I'm going to have to pay for the soundness error of the original PCP, so there you go. But whatever additional costs I have from the consistency check, I can drive them down to epsilon. And I'll pay a little bit in some number of repetitions of this local decoder. How many? Well, this many. We'll see later, just like some Chernoff bound. And I'm going to be able to achieve the desired proximity parameter that I wanted. Whatever proximity parameter I want, I'll pay for it here and here. Okay? So don't mind too much the same expression. The expressions, the main point is that basically almost nothing changes here. I'm just paying a little bit more in queries here, and I've gained now proximity parameter. Okay? So the construction is actually pretty simple. The PCP of proximity is just going to consist of the PCP with no auxiliary proof, because we have a local decoder. The local decoder, is happy to be fine with just the noise encoding. And the PCPP verifier is going to run the PCP verifier, and then it's going to run the local decoder on a bunch of indices. Okay? Why? Well, if the given W and the encoded W are delta var, and I sample a random index and I compare them, then I should spot a different location with probability delta, right? And if I do this t times, this probability that I never find an inconsistency will grow down, will kind of decay exponentially in t, right? And of course, the local decoder itself has some error, and that's why, that error I have to account for it also somewhere, okay? And, we're doing the analysis in the next slide, but, is the construction clear? It's pretty kind of straightforward, right? We have the candidate witness, like in the bad case, it is delta var from the thing that it's going to be inside this noisy encoding, and I'm just going to compare them at a random index, okay? Some number of times. All right, before we analyze this, let's just kind of make sure people are on board.
Just like a small detail on the second point, should it be d to the I tilde?
Second point.
Second point on the definition of a local decoder.
D to the I tilde. No, I is just the desired location, so I give it as input.
Sorry, I meant like the superscript. Should it be I tilde?
Oh, that's yeah, sorry, totally. Sorry about that. Yeah, this is that's the noisy one. Sorry. Yeah. And this should be a tilde as well. Thanks. All right. So more questions while you can. So again, intuitively what we're doing is we're just acknowledging the fact that the PCP already has a witness, but it's not like literally lying there. It's like maybe it's encoded, right? And even if it was literally lying there as part of the encoding, these things are called systematic encodings. It might be a small fraction of the whole encoding, so a bit of noise may just completely drown the witness away. So we're going to have to locally decode, right? Because a random index of the message may be a much smaller percentage of the encoded message, and the noise is a percentage of the encoded message, right? So we cannot afford to just look at that part. We're going to have to rely on a local decoding procedure that for a fixed I it's going to do well. Okay? All right, hopefully that made sense. Please stop me, because we're about to analyze this. Okay?
Should we think of the local decoder as making like constant number of queries per index?
You can think constant or small, right? We've seen both. Constant, it's going to be for linear functions. Small is going to be for low-degree functions. We can't afford, we cannot do it in constant number of queries there. Yeah, and also local decoders are like, you know, like it's specifically about a small number of queries of some sort. Otherwise, you just like open up the message and see what's inside, right? And you just answer. All right. So also another thing to keep in mind is that this decoding radius, this decoding radius here, usually it is smaller than the unique decoding radius. Though it could be even smaller than that, depends on what the analysis shows, right? So it could be that the local decoder like doesn't quite work up to the unique decoding radius, it's just gonna get stopped somewhere earlier, but that's okay. All right. So I also want to say why that's okay, because this condition, that's fine, because if you go back to our analyses, we showed such things, such PCPs, basically for any constant delta. So you could have made delta to be arbitrarily small and nothing would have changed. It would have just affected slightly epsilon PCP with some, you know, some larger like soundness error. Okay, so here's the construction again, and let's analyze it. So for completeness, if x and w are in R, then by completeness of the PCP, then this PCP verifier will accept, say, with probability 1, or 1 minus the completeness error. And since in the good case, the first part of the PCP really is an encoding of the witness, by completeness of the local decoder, no matter which index you're going to pick, these things will equal, right? Because you're going to be comparing the W that is outside and the decoded value of the W that is inside, but those are the same things. And the local decoder has perfect completeness. So we're done, okay? So the interesting part is, you know, what happens if W is delta far from all valid witnesses for the instance X. So now, you know, somebody writes down an arbitrary PCP of proximity. So here it is. So an arbitrary candidate encoding and an arbitrary candidate proof for satisfiability. Now, two things could hold. Either the PCP verifier accepts with probability there is at most epsilon PCP, at which point you say, okay, whatever, it doesn't matter what happened, you know, we're fine with that, okay? For example, maybe the X is not in the instance. So X is not, the instance X is not in the language. Maybe that's what happened. Or maybe something else happened, it doesn't matter, okay? Or in the other case, if we know from the kind of property of the PCP that if this probability is above that, then we know that we must be in the case where X is in L, and also this first part of the PCP is delta PCP close to some encoding of some valid witness, okay? And we're using this property of this epsilon delta enc soundness, okay? If that is the case, now we have to kind of understand what happens, because remember that like we still have to reject with high probability, so something's going to have to save us. This guy has to save us. So let's argue that. So in the latter case, because a delta PCP is less than the unique decoding than the decoding radius of the local decoder, I know that for every choice of index, I will have this property that when I decode pi a hat, I will find w hat I, right, at index I, with this probability for any I, okay? Notice that this is w tilde, not w, because that's what's inside, that's what inside this noisy code word, okay? Also, because w is delta far from all valid witnesses, w is also delta far from this particular valid witness. So, there's no I here. So the probability that these agree is at least delta, right? at a random index. Okay, well, the probability that the verifier accepts is bounded from above by this guy, or the probability that I don't notice a difference in any of my runs, well, that would be this quantity. Okay? All right. And then, if I just pick t to be, that quantity, then, this entire thing becomes at most epsilon. And this is just, standard setting of, how to kill this type of things and make them, to make this one less than or equal to epsilon. This is how many repetitions you should have, okay, by t. No, it's not even a Chernow bound here. Okay, so that is how we construct PCPs of proximity from special two-part PCPs and a local decoder for the encoding of the first part. Okay, so this was like an abstract construction, and we can instantiate it in two ways. We can construct an exponential size constant query PCP. How? Well, in the past, we constructed an exponential size constant query PCP for quadratic equations. The encoding that we used was linear extensions. And observe that, the soundness analysis, if you go back, showed that it was epsilon delta enc sound for this enc, really for any delta below the unique decoding radius. And we showed that. And also, this particular enc, namely linear extensions, linear functions, have a local decoder. And the local decoder, you're just basically, whatever location you're interested in, you just take a random decomposition, right? And, maybe because I may be interested in boosting my error, I'm just going to do that a few times and I take a plurality, right? Because as I take more and more, because this probability is like, say 75% or something like that, I do it more and more, the fraction of answers that are going to concentrate around 75% of the answers being the same correct value, okay? And it's going to concentrate exponentially fast around that. So in particular, if pi tilde is delta LD close to some enc of A, then the probability that this decoder says the wrong answer is bounded from above by this. Now I'm using the Chernow bound. And again, you have like some similar expression. Remember, this 2 here was here because this guy ends up in a noisy part with probability delta LD, and this also ends up in a noisy part with probability delta LD. Each of these is individually random, and so you pay a 2 delta here. And so when you don't land there, that's when you answer correctly, okay? Yeah, and the rest is just a Chernow bound. So if we focus, let's say for simplicity, on binary fields, and you apply the lemma from the prior 2 slides to this PCP and this local decoder, you're going to get this first result that we claimed in the first slide. Okay, for any delta greater than 0, you get these things. Okay, and you notice that the 1 over delta here is coming from this 1 over delta. Well, again, it was already from the previous one. Sorry, it was already from the previous one. That was pretty simple, right? So like once we understood abstractly, what tool we wanted, here we just had to instantiate. Okay. Any questions about this local decoder? Okay. By the way, we already used it once. Like we used it for compiling linear PCPs into exponential size PCPs. So if you want polynomial size polylog-query PCP of proximity, then okay, well, we constructed a poly-size polylog-query PCP for quadratic equations. In that case, we used multivariate logic extensions, okay? With some certain number of variables and a certain degree. That's the total degree. And again, the analysis showed that we had this 2-part PCP that, if you're above a certain threshold, that it means that the encoding was basically some noisy. The first part of the PCP was some noisy encoding of a valid witness, okay? And also we have a local decoder. This is something that you've seen in your homework. One way of doing it is you have these magical constants, right, related to derivatives. You're gonna kind of look at the location you're interested in, right? So I have to, of course, convert my index I, which is an integer between 1 and w, to ei, which is just some, the correct location in the hypercube, right? And I have my randomness here is like the random step size, right? And we had this kind of self-correction procedure related to the loaded test, right? And you have analyzed this in your homework. Now, because we're doing plurality, I have the same like a similar expression, except that the 2 now becomes d plus 1 because I'm touching a delta noise function at d plus 1 locations. So now I have this bigger loss, and now I have like some bigger expression here. It also does mean, by the way, that I need to set my sort of my decoding radius in this example is well below the unique decoding radius, because it has to be like 1 over, let's say, I don't know, 2d plus 1. Okay, once we do that, we get the other PCP of proximity. Here it is. Polynomial size, polylogarithmic query complexity, and now we have a proximity parameter that we can control. Again, it's just the same paradigm instantiated, just in different regime. Okay, and conveniently, kind of literally the same construction, just different encodings. Questions about this? Okay, I mean, you probably become ninjas about these things, so I hope that's the case, and they're not confused. Because now we have something strictly harder. It's a proof sketch only, but we have to talk about it. In the composition theorem that we're about to state, we're gonna see we have to apply composition twice. So we need one component to be both robust and proximity. Okay, so we've seen how to make things robust, we've seen how to make things proximity, but we need something that is both. Okay, and yeah, it's kind of annoying. And it can be done. So, here's the theorem that you get. We're going to need it just for the polynomial size polylogarithmic query regime. And we need both proximity and robustness. And robustness, it's okay if it's like some fixed thing. I do need the proximity to kind of go as small as I want it. And the proof sketch is that last time we showed how via query bundling and robustification, how to construct some robust PCP for NP, in this precise regime, right? And because the starting PCP that we robustified had this epsilon delta enc property, then you can see that after robustification, it wasn't lost. It's still the case that it has this property. Like now you have a robust PCP for quadratic equations such that when your robust PCP verifier accepts with high enough probability, it means that one part of the PCP is close to a noisy encoding, is close to an encoding of a valid witness. Okay? All right, so therefore, for us to not mess up robustness, it suffices to augment this one with a robust encoding consistency test. Okay? It's basically what we just did, but we want to do it in a robust way because we're starting from something robust and we don't want to mess it up. Okay? Now, we know, again, from that condition that this first part is going to be delta close to some valid witness, encoding with some valid witness. And basically what we can do is we can just take the idea that we worked out and we're just going to apply like some bespoke query bundling robustification to the specific consistency like sub-protocol we just designed. I'll just sketch this because I already spent enough time preparing slides, and so this one I didn't have time to like fully work out, nor I think you want me to. Intuitively, the prover is going to provide for every index I and for every choice of random field element, an encoding, this is a different type of encoding. This is like encoding according to good code. This is like a robustification part of the coefficients of a polynomial that encodes a random query about the index. So let's kind of parse this for a moment. This one here is the polynomial that interpolates I at 0 and is equal to R at 1, right? So this is a function that is I at 0 and 1 and R at 1, right? Good. So it's a random polynomial, okay? And now we have this, remember, in the query bundling step from last time, we had this way of bundling up queries into randomized questions, right? That's how we bundled up queries. After we bundled them up, we took the bundle and we encoded it to break it back down into like the smaller alphabet, but in a robust way. So now the prover is going to give me basically the encodings under a good code of the bundles associated to the random consistency test. Okay? And so now the relaxed local decoder is basically, it's a local decoder with a proximity proof. Because what it's going to do, like before, it's going to sample the, how to say, the randomness that randomizes the question, and then we're going to look at the bundle at 0, okay? It's going to give us the answer, which is I, right? And where do I get the bundle? I get it by decoding the code word, okay? But also I need to make sure the bundle has something to do with what I'm talking about, and so I test it at a random point like we did last time, okay? So last time, remember, we were kind of retrieving the queries from the bundle all at once, right? In a kind of robust way, right? But, you know, there was a super constant number of things, so I had to encode them so that I had robustness, right? And in order to make sure the bundle has something to do with my sort of noisy code encoding, then we ended up, we ended up like testing it at a random point, okay? So this one, I don't want to linger too much, but it is basically, I'm just borrowing ideas directly from the query bundling robustification that we did generically, and I'm just like directly applying them to the consistency check that we just did, okay? I think it's a good exercise if you want to try to do it, to work out the proof in detail. It will be like a combination of ideas from this lecture and from the last lecture, okay? All right, so we did this, and are there any questions? Because we're about to prove the PCP theorem. We now have all the ingredients we need. I think I'm doing well on time. I was going a bit fast possibly because I felt like I had more material than usual, but maybe I really did breeze through it. So if you want to ask some questions, we're about to shift gears and talk about how to prove the PCP theorem with these tools.
I actually just wanted to sort of check back in on that one point. I think someone else had asked a question about this, but I might have missed the substance of the answer, because with regards to local decoders, and you had noted that when we have linear input, or a linear function, we can get constant local decoding sample complexity, right? And then when we had low degree polynomials, however, it was small. And what I guess was the concept of small in that case, and like basically like say in the context of a PCPP.
Yeah, so it was, yeah, so let me go there. Small means d plus 1, as you can see here. And you know, where d is the total degree. And what is the total degree? The total degree is polylogarithmic, because if you remember, well, d is number of variables times the side of the cube, right? And number of variables is log n over log n, right? And the size of the cube usually was log n. So in that case, the number of queries would be on the order of log squared over log n, which is small. And that is why we get polylog n here. Okay. Good question. More questions?
So just to be clear, like the T that we saw in like the last two protocols, that's what shows up as QE here, right?
Yes. Yeah. Well, I mean, it's an additional thing that shows up, right? Because the PCP we start from already has query complexity polylog, and we're just adding more polylogs.
Right. And same with the constant one. It was already constant, and we're adding just
more constants. Yeah. Okay. All right. So now we can prove the PCP theorem. So what is the PCP theorem? Well, it's the regime of polynomial size and constant query complexity, of course, specifically over the binary alphabet. Okay. So, and again, just as I explained sort of 2 lectures ago when we started talking about proof composition, this is putting together the best of both of the PCPs that we constructed. Okay. Now here's the proof attempt first. So one idea would be to apply proof composition theorem with, and also I'll fix perfect completeness and soundness error half and the same alphabet from now on the same. So one idea would be to say, okay, well, we need an outer PCP that is robust. We're going to pick the one that has good proof size, okay? And that's in fact the one that we built from last lecture. And so here it is. So it says that we have a PCP of polynomial size, polylogarithmic query complexity, and I'm going to introduce this term of like state size. That's just basically like the size of the instance that is going to be about the next, the relation of the inner verifier, right? And we have some constant robustness parameter. The inner PCP has to be a PCP of proximity, which we built today. And the idea intuitively is to say, okay, well, let's use the exponential size constant square PCP, right? Because remember, composition is the composed PCP will give you the proof length at high level intuitively. It's going to be the proof length of the outer PCP and the query complexity of the inner PCP. So we want to put kind of the poly size many query thing outside and the exponential size constant query thing inside. So here it is. And today we built this one, okay? Now remember that for proof composition to make sense, you need the robustness of the outer to be at least the proximity of the inner, but that's okay. We can, we've constructed PCPs of proximity that we can make the proximity as small as we want. So do that. Now we're gonna set the size of the inner thing to be like the size of as determined by the size of the inner thing for the relation of the outer verifier. And we're gonna get a PCP whose length is the outer one plus 2 to the R out inner one. And if you see, well, because R out, because L in is exponential in the state size of the outer one, okay? Now the outer one though has state size that is polylogarithmic, okay? That's just because the outer verifier is thinking about a polylogarithmic number of queries. So the instance size of that problem is of polylog size. So if we pay exponentially in that, we're going to get a proof that is n to the polylog n, which is not polynomial. We're going to get constant query complexity, but this PCP is too long. Okay? So now if we had logarithmic here, that would have worked, but if you kind of dig inside, like it's just not logarithmic at all. Like it's at best like log squared over log n. It's totally not log n, okay? And that's at best. So this kind of naive composition of poly-size polylog query outside and exponential size constant query inside doesn't give you poly-size PCP. But that's okay. Here's the idea. We're first going to compose. We're going to do composition twice. First, we're going to compose the poly-size polylog query PCP with itself to reduce the state size and the query complexity. Okay, really the state size. To go from polylog to polylog-log. All right? And then, once we're at polylog-log, we're going to compose the result with an exponential size constant query PCP. Okay? And in particular, because we have this middle guy that serves both as inner and outer, right? Or at least the inner kind of becomes, like, we need the composed thing to be robust. That means that the inner of the first composition has to be both proximity and robust. That's why we needed that. Okay? So that's what we're going to do. So now we actually do that. So part one will be the first composition. We're going to apply the proof composition theorem, where the outer is the robust variant of the poly-size polylog query PCP for NP. So nothing has changed. But now we're going to use the robust and proximity variant of the poly-size polylog query PCP for NP. That's the one we built today, where we have both robustness and proximity. Okay? And now, again, provided this is the case, which we can do because we can make this as small as we want, we're going to construct something that still has polynomial size, but now the query complexity and the state size are polylog-log. Okay? Why? Because, look, the state size here was polylog. Here we pay, the new state size is going to be polylog of the instance we're talking about. That's going to be polylog of polylog. Well, that's polylog-log. Okay? And the proof length is all fine, right? Because we have polynomial plus 2 to the log, that's polynomial, times poly of this thing, but that's polylog, so it's polynomial times polylog-log. That's okay, still polynomial. So yeah. So now we have this sort of PCP that is robust. So we can use it as an outer for the next composition. Why is it robust? Because we had the inner one that was robust. And remember, we proved this proximity and robustness preservation. When the inner one is robust, then the composed one is also robust. Okay, we proved this like 2 lectures ago. So, yeah. So we use the fact that if the inner PCP is robust, then so is the composed PCP. And we must keep track of the state size for the composed PCP because we're going to be using it in the next sort of composition. So the next composition, now we're going to use this poly-size polylog-log query robust PCP for NP obtained from the first composition, and here it is. And now we use the proximity variant with exponential size constant query PCP. Here it is. This is the one that we couldn't use the first time around. And now, again, making sure that things work out. Now we have 2 to the R out, which is polynomial, and then we have exponential in poly log-log. Well, that's polynomial. Okay? So, and the query complexity is constant, and we're good. All right? So we just had to kind of first get to the polylog-log regime, which by itself is a new result, right? Because we hadn't seen that regime yet. And then once we were in the polylog-log regime, we're at a point where it was feasible to use the exponential size PCP. Okay? So that is the proof of the PCP theorem. As a bonus, if you had started, you can also construct PCPs of proximity in the same regime. Okay? I guess I forgot to mention, yes, front of you delta here. As a bonus, you can also get this as well because we could do the similar two-step composition, but we start from the outer PCP that is robust and a proximity proof, which guess what? We already have it because we were using it as the inner for the first composition. And both compositions will preserve the outer's proximity. And so we end up with a PCP of proximity with polynomial size and constant query complexity. Okay, that was basically for free. Questions? I'm sure there are some, so please ask questions. So in the meantime, this is a good time for me to stop the recording.